In our previous episode, we explored three important distance metrics. Manhattan distance, which calculates absolute differences, Euclidean distance, which measures straight line distance, and Minkowski distance, a generalized form of both. In this episode, we will dive into three more similarity measures. Cosine similarity, which evaluates the angle between vectors. Hamming distance, which counts differing elements in sequences. And Jaccard similarity, which compares the intersection and union of sets. Let's start it. Cosine similarity measures the cosine of the angle between two vectors in a multidimensional space. It is widely used in text analysis, recommender systems, and other applications where the orientation of vectors matters more than their magnitude. Let us visualize two vectors in a 2D space to understand how cosine similarity works. Here are two vectors, labeled as vector A and vector B. The angle between these two vectors determines their cosine similarity. A smaller angle indicates higher similarity, while a larger angle indicates lower similarity. Cosine similarity is calculated using the dot product of the vectors divided by the product of their magnitudes. The formula is cosine similarity equals the dot product of A and B divided by the product of the magnitudes of A and B. Now, let's dive into an example. Consider a text analysis task where we want to compare the similarity between two documents. Each document is represented as a vector of word frequencies. To compute the cosine similarity, we first calculate the dot product of the two vectors, then divide it by the product of their magnitudes. First, we calculate the dot product of the two vectors. This is done by multiplying corresponding elements and summing the results. Next, we calculate the magnitudes of both vectors. The magnitude is the square root of the sum of the squares of the vector elements. Finally, we compute the cosine similarity by dividing the dot product by the product of the magnitudes. The result is approximately 0.86. A cosine similarity of 0.86 indicates that the two documents are quite similar. This metric is particularly useful in text analysis, where the magnitude of the vectors, word counts, may vary, but the orientation, relative word frequencies, is more important. Cosine similarity has notable characteristics. It is invariant to the magnitude of vectors, making it ideal for text analysis and sparse data. However, it does not consider the magnitude of vectors, which can be a limitation in some applications. Cosine similarity is widely used in various fields. Some of its key applications include text analysis for document similarity, recommender systems for user item similarity, and information retrieval for query document matching. Hamming distance measures the number of positions at which two strings of equal length differ. It is widely used in error detection, coding theory, and DNA sequence analysis. Let us consider two binary strings of equal length. We will calculate the Hamming distance between them. To compute the Hamming distance, we compare the two strings position by position. We count the number of positions where the corresponding bits are different. In this example, the two strings differ at 2 positions. Therefore, the Hamming distance between them is 2. Now, let's dive into a practical example. Consider a scenario where we want to detect errors in transmitted data. We have a transmitted binary string and a received binary string. We will use Hamming distance to identify the number of errors. We compare the transmitted and received strings position by position. The Hamming distance will tell us how many bits were flipped during transmission. In this example, the transmitted and received strings differ at 1 position. Therefore, the Hamming distance is 1, indicating a single bit error. Hamming distance has notable characteristics. It is only defined for strings of equal length, is computationally simple, and is widely used in error detection and correction. However, it does not provide information about the magnitude of differences, only their count. Hamming distance is widely used in various fields. Some of its key applications include error detection and correction in data transmission, DNA sequence analysis, and coding theory. Jaccard similarity measures the similarity between two sets by dividing the size of their intersection by the size of their union. It is widely used in text analysis, recommendation systems, and other applications where set-based comparisons are required. Let us consider two sets, set A and set B, containing some fruits. To compute Jaccard similarity, we first find the intersection and union of the two sets. The intersection contains elements common to both sets, while the union contains all unique elements from both sets. Jaccard similarity is calculated as the size of the intersection divided by the size of the union. The formula is Jaccard similarity equals the size of the intersection of A and B divided by the size of the union of A and B. Now, let's dive into an example. Consider a text analysis task where we want to compare the similarity between two documents. Each document is represented as a set of unique words. To compute the Jaccard similarity, we first identify the intersection and union of the two sets of words. The intersection contains words common to both documents, while the union contains all unique words from both documents. Here, the intersection contains banana and orange, which are common to both sets. The union includes all unique words from both sets: apple, banana, orange, grape, kiwi, and mango. Finally, we compute the Jaccard similarity by dividing the size of the intersection by the size of the union. The result is approximately 0.33. A Jaccard similarity of 0.33 indicates that the two documents have some similarity, but it is not very high. This metric is particularly useful when comparing sets where the presence or absence of elements is more important than their frequency. Jaccard similarity has notable characteristics. It is ideal for comparing sets where the presence or absence of elements is important. However, it does not consider the frequency or magnitude of elements, which can be a limitation in some applications. Jaccard similarity is widely used in various fields. Some of its key applications include text analysis for document similarity, recommendation systems for user item similarity, and bioinformatics for comparing genetic sequences. Let's compare cosine similarity, Hamming distance, and Jaccard similarity. We'll explore their formulas, use cases, and key properties. Here is a table summarizing the differences. Cosine similarity calculates the cosine of the angle between two vectors. Hamming distance counts the number of positions where the corresponding values differ. Jaccard similarity measures the overlap between two sets by dividing the size of their intersection by the size of their union. Cosine similarity ranges from -1 to 1, where 1 indicates identical vectors. Hamming distance ranges from 0 to n, where n is the length of the vectors. Jaccard similarity ranges from 0 to 1, with 1 indicating identical sets. Cosine similarity is widely used in text mining and high-dimensional data. Hamming distance is ideal for error detection in binary data. Jaccard similarity is commonly used for comparing sets, such as in market basket analysis. Cosine similarity focuses on the orientation of vectors rather than their magnitude. Hamming distance is sensitive to the exact positions of differences. Jaccard similarity ignores the absence of elements in both sets, focusing only on their presence. This concludes the comparison of cosine similarity, Hamming distance, and Jaccard similarity. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up, subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.